called the cosmic microwave background. Now, to organize this, I have the notes up here already. So I will be defining for you what the cosmic microwave background is. So we'll do that first. The cosmic microwave background, or CMB. So if you hear people in cosmology or physics talk about the CMB, this is what they mean, the cosmic microwave background. And it is an extremely important thing in cosmology. As you can imagine, cosmology is kind of hard to do. Like, given that the universe is almost 14 billion years old, it's kind of hard to picture the universe at a much earlier time or when it was getting started. Because we have the cosmic microwave background, as we shall see, these are photons from a very early time in the universe. This actually quite literally gives us a picture of that early time. So this is why it is of extreme significance in cosmology, and people like to learn about these constantly, or people like to learn things from the CMB constantly in cosmology. It's a very important topic. Talk about that star-based station. I don't know what you mean. Be more specific. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang. So it is photons that are kind of just hanging out from that early time in the universe that we can still see. And it is isotropic and it's homogeneous. No matter where you look, you still find it. So this CMB fills the universe with a nearly uniform glow of microwave radiation. So when we look now, the photon wavelength is actually in the microwave wavelength, okay? So as you know, photons, or light, has lots of different wavelengths depending on which light, like the optical light versus microwave light versus gamma rays versus X-rays have all different wavelengths. This CMB, we see it in microwaves, okay? Discovered by Arno Penzias and Robert Wilson in 1965. So CMB at this point is well understood to some extent because it's also old, but it's still a source of learning for many, okay? So discovered in 1965, this signal provided landmark evidence for the Big Bang theory. While the CMB appears extremely smooth, which by smooth, what we mean is the same in all directions to about 1 part in 100,000. So we can actually define out what smooth is, because it's not completely perfectly smooth, but it is smooth to 1 part in 100,000. So there are little perturbations, there are little spots of overdensity in the CMB, turns out, but for the most part, it is very smooth. So imagine, I mean, when they first saw it and they were studying it, they thought it was very smooth, and I mean, how did anything happen? But then they found that there were actually certain overdensities, but we'll get into that. Sensitive instruments have detected tiny temperature variations, which are imprints of primordial density fluctuations in the early universe. So this is that part, which is that you have to be a very sensitive instrument to pick up on these fluctuations, which are the spots of overdensities, like I was mentioning, because if you didn't have any overdensities, then how would you make galaxies? Because the spots of overdensities later on clumping more would become the galaxies that, like I was mentioning earlier, in connection with large-scale structure topic in cosmology.